So now we get to the idea of what is a limit. We've talked about this already a little bit. A limit is a value that you can get really, really close to. And sometimes limits are really easy to evaluate. For example, this is the notation. We say the limit as x gets close to 5, or as x goes to 5, of 3x minus 8 would be 7. If you think about it, if you put a number in there close to 5, does it make sense that it's going to be close to 7? And if you can plug in the number directly, which you can in this case, that will always be the limit. What happens if I plug in 5 for x? 15 minus 8, I get 7. Right? If it's equal to 7 when you plug in 5, chances are when you get close to 5, it's going to get close to 7. So the limit as x approaches 5 of 3x minus 8 is equal to 7. And in this case, if you can plug in that value, that's going to be your limit. The idea of a limit, if I graphed 3x minus 8, well, that would have a y-intercept at minus 8 and a slope of 3. That would be a line that would look something like this. And it happens to have the point 5, 7 on it. The way that a limit works is it's saying, as you get close to 5 from the left side, so as I get close to 5 from the left side on this line, and as I get close to 5 from the right side on this limit, does it go to the same number? Do I get close to 7 in both directions? And the answer in this case is yes. And that's why the limit would be 7. We're going to get some interesting questions where the graphs are broken apart, and then sometimes the limits do exist and sometimes they don't. Some definitions. Our first definition is continuous. This is not the mathematical definition of continuous. This, if I pull out my math dictionary over there, you won't find this written this way. But if you can draw a graph without having to lift your pencil, it's continuous. If you have to lift your pencil and start again on the other side, like if it has a hole in it, then it would be not continuous. Or if there's an asymptote, you have to lift your pencil and draw something on the other side, that would be an example of something that's discontinuous. But anytime we have a continuous graph, you can find any limit at any value on that graph. And that's just simply plugging it in. So here we have x squared minus 1. That's a parabola. Can you imagine drawing the whole parabola in one swoop without having to lift your pencil?
You wouldn't be able to start if you wouldn't be able to start from the side, right?
Well, okay. You could just go backwards and there you're good. So the limit as x gets close to 2 of x squared minus 1 is going to equal 3. Boy, yesterday's lesson was a little heavy with some algebra, and now we're feeling good again. This is, I'm like, yeah, it's like hit you down, then build you up again, and then you're feeling good, and then boom, boom. No.
Isn't that what all teaching is?
That's what So those limits are so easy that we don't do too many of them. What we're more interested in are these 0 over 0 limits. And I'll tell you why I call that in a second. But first, here's another definition. Something's discontinuous. It has a non-permissible value, or you can't draw it without lifting your pencil. So we have something with a hole in it, or something with an asymptote. Those would be examples of graphs that are discontinuous. So when we have non-permissible values, we have graphs with discontinuities. So in this example, When I plug in x equals 3, it's a non-permissible value. It doesn't exist on this graph. Would the value of x equals 3, thinking of grade 12, would this result in an asymptote on this graph, or would this result in as a hole in this graph? Okay, right. It has a hole, and we remember that a graph would have a hole because when a factor simplifies, it always results in having a hole. And after we simplify this, this equation would just become the limit as x goes to 3 of x plus 3. Well, can you plug in 3 now? Yes. It would equal 6. And that is connected to, on this graph would have a hole at 3, 6. And so as you get close to 3 from both the left side and the right side, the graph would get close to that hole. And so that's why we would say the limit of this expression is equal to 6. So that's a connection between what you were doing in your grade 12 year and limits. Now, the reason these were called 0 over 0 limits is if you didn't simplify this and you plug 3 into your numerator, can you see your numerator is equal to 0? Yeah. And 3 into your denominator is equal to 0. Right? And so now we've just proven that 0 divided by 0 is equal to 6. Well, that's not always the case. But in this case, it is.
Is it equal to 7 sometimes?
It could be. We could make it equal to anything we wanted, depending on the equation. Right? That graph has a discontinuity at x equals 3. We already discussed how it has a hole at x equals 3, and that function is undefined at that point. What happens when you plug in -2 into this equation? The top is equal to 0. The bottom is equal to 0. So we've got another thing where we can't figure it out by plugging it in. We're going to need to simplify this so that that non-permissible value goes away. Can you see that the bottom can be factored? Notation-wise, as I'm working with a limit, I need to write limit as x goes to -2 all the way until I can actually plug it in and evaluate it. So if I'm going to factor the bottom here, x plus 2, x plus 4, I still have this x approaches -2 there. And so we can see on the bottom why -2 is a problem. It's causing us to divide by 0. What do you notice about the top? It's a cubic thing. Nice. It's a sum of cubes. So if we go to our formula for that we had from before, we can factor out an x plus 2. How convenient. What are we left with in here?
X squared minus 2x.
X squared minus 2x plus 4. And now the value that was a problem goes away. Now what happens when I plug in -2? The bottom is going to be 2. The top, 4 plus 4 plus 4. And so our limit is 6. Hey, 0 divided by 0 is 6 again. This graph, again, if you were graphing that original graph, it would have a hole in it.
2 and 6.
Okay? It would have a hole. It would have an oblique asymptote. Remember all of that stuff? Yes. plug in 0. We got 0 on the top, 0 on the bottom. So you're going to have to play around with this equation. How can you manipulate this equation so that that h disappears and you can actually plug in 0? I would say 90% of you expanded this like this: h squared minus 6h plus 9 minus 9 equals h. Your 9's canceled out. You factored out an h out of what was left so that your h is simplified. Notice we write the limit as h goes to 0 until we get to a point where we can actually plug that value in. And at this point, you could plug it in and get negative 6. What made me really happy is that a couple of you came up with another technique and you said, hey, the top is a difference of squares and I can factor it. So what does that do for me? And this is the thing about these questions. You're going to have a question and you need to play around with the equation, and there might be more than one way to go about that. So if you recognize that as a difference of squares, well, it's going to be h minus 3 plus 3 and h minus 3 minus 3 all over h. That's what factoring would look like. And at first you might think, wow, that just made things look more complicated. But if you simplify in here, the first one just becomes h, the second one h minus 6, and we get the same result as before. To me, that makes me excited. That is a beautiful question that can be done in two different ways. And to do something where this is not your normal form of a difference of squares that you're used to, but you can still do that, which is a really cool thing, in my opinion, about math. Okay. How's working on the last one going? When we rationalized the numerator in our notes the other day, you were like, when would you ever want to rationalize a numerator? Well, here's an example. Rationalizing the numerator allows us to simplify, and after simplifying, we can then evaluate the limit.